Test. Test. 3, 2, 1. This video illustrates how to solve an optimization problem where a new constraint is introduced partway through the process. When you get a problem like this on your exam, it will already be partially solved for you, like this one. The x and y are defined, and the graph already exists with the constraints graphed, the polygon found, and the vertices identified. The first thing you have to do is define the optimization function. If tickets cost $2 per student and $5 per parent, and students are x and parents are y, then the optimization function is 2x plus 5y equals z. The next thing you do is start building your table using the vertices that are already identified in the graph for you. Here's my table. The three vertices, 20, 20, 120, and 2100, are already in there. And I plug all three of those vertices into this optimization function. I get these answers, 540, 140, and 300. If this problem was complete, I would have my answer now. Since we're trying to maximize profits, I picked the largest number. $540 would be the maximum profit, and it would be earned by selling 20 tickets to students and 100 tickets to parents. But the school has decided to introduce a new constraint. The school has decided there should be at least as many students present as there are parents. That changes things. What we have to do next is make an inequality that matches this new constraint. And my inequality is going to be defined down here. My new constraint is x greater than or equal to y. I will not show the table of values. 3, 2, 1. I will not show the table of values because that is explained in other videos on this website. But if I were to graph this new constraint, this is what it would look like on my graph. The new line is this blue line, and it is shaded below and to the right. That changes the shape of my polygon. It creates a new vertex, which I have right here, and the new vertex is x equals 60, y equals 60. This large yellow rectangle, this 3, 2, 1. This large yellow rectangle is no longer my polygon, because it includes this region up here, which is not shaded by the new line. So I'm going to shade a new polygon in a different color so that we can see what the polygon looks like now. Here, shown in green, is my new polygon. Here, shown in green, is my new polygon. It has three vertices, the 20, 20, and 120 that we always had in this situation, and the new 60, 60. The old 2100 has been eliminated. Going back to my table, I have to show that the 2100 vertex has been eliminated by drawing a line through it in the table. This will stop me from accidentally including that vertex in my new answer. And I have to make room in the table for a new vertex. So I add a line to my table. I put the new vertex 60, 60 into it, and I plug 60, 60 into the optimization function, and I get this new answer of 420. The new answer to the situation is 420, but I have to be careful how I answer the question with this type of problem. The question was, how will this affect the event's maximum profits? So it's not enough to just say the maximum profits are 420. You have to say a new answer. No, 3, 2, 1. You have to say what the effect was. The maximum profits have decreased by $120 from the old answer of $540 to our new answer of $420. And this will be achieved by inviting 60 students and 60 parents to the event. This is what you do when you're given a problem where a new constraint has been added partway through the situation. Cut.